Hi everyone, welcome back to chemistry. In this video, we're going to start chapter 7, which is all about energy and chemical processes. I apologize if my voice sounds a little funny. I'm getting over a cold, but I hope it's not too distracting. So let's talk about energy first. So we're pretty familiar with energy. We talk about it quite a bit. It's part of our daily lives. But what is it in terms of, chemistry? So we say that energy is the ability to do work. So anytime you have to do any work, there's always going to be some kind of input of energy involved. Energy can also be transferred from one object to another if the objects have different temperatures. And the transfer of energy due to temperature differences is what we call heat. So this person looks like they're grilling some food, and that food, when you put it on the grill, is not cooked, and we use heat energy to heat it up and to cook it, and so we can actually eat it. There are different units for energy. The SI unit of energy, work, and heat is the joule. So that's how we measure energy, is using units of joules, typically. What is this? Joule is kind of a funny looking word. When we abbreviate them, we use a capital J. So capital J. And just like any SI unit, we can put prefixes in front of that unit. So for instance, killi, like we can put kilojoule or killi in front of joule, and that turns into a kilojoule. But a joule is a very tiny amount of energy. It's really, really small. For instance, it takes about 4 joules to warm just 1 milliliter of water by 1 degree Celsius. So that's not much energy. Another unit of energy that we use more frequently, especially in health professions and in our everyday life, is the calorie, abbreviated CAL, lowercase c, A-L. And 1 calorie equals 4.184 joules. Now, because joules are pretty small, calories with a little c they're also very small. So a lot of times when you look at the food label, something like this over here, when you look at a food label on your food, calories are actually represented with this big C calorie here. And big C calorie is actually kcals. So anytime you see a capital C here instead of a lowercase c, it's actually referring to kilocalories, because 1 kilocalorie equals 1 capital C calorie. And that's just to kind of keep this number a little bit lower. If we were representing that number in just little c calories, that would be quite a long number to write out. So we use kilocalories or capital C calories to represent those numbers in a little bit more of a compact way. All right, so sometimes we're going to have to convert from calories to joules or joules to calories, and we can use this conversion factor to do that. So let's try this out. Whoops. So this practice problem says an apple is 95 calories, big C calories, so noting that that is a capital C, which means that we need to think about, that's kilocalories, not just calories. So in 1 calorie, there are 1,000 calories, right? Or you could think of this as a kilocalorie, right? And in 1 kilo of anything, right, there are 1,000 little things. All right, so an apple is 95 big C calories. Convert this amount to little c calories and then to joules. So we start with 95 calories as our first conversion vector. And then our next one, it looks like we need to go from calories to big C calories to little c calories in order to get to joules, right? We have to go through little calories to get to joules. So let's do that. So we're going to convert first from big calories to little calories, I guess I'll call them. So from big calories, so 1 capital C calorie is 1,000 little c calories. So now we can cancel out the top and bottom, and then we'll have, now we're in little c calories, which is great because we know a conversion factor that connects little calories to joules. So we'll go 1 little calorie is, and I'll just actually write it out, is 4.184 joules. And you don't need to memorize this conversion factor. I actually meant to mention that earlier. You don't need to memorize it. That will be given to you on an exam if you do need to use the equality here. Okay, so let's see here. Sorry, excuse me, my sniffling here. So let's see, we've got 95 times 1,000 times 4.184. That's a lot of joules. And that kind of makes sense, right? Because joules, we said, are a small unit. All right, now what about heat and temperature? We've talked about energy, but what about heat? So temperature is a measure of how hot or cold an object is relative to another object. So for instance, when you're holding this kind of like hot cup of, this looks like a caramel latte or something, a hot cup of coffee, the reason you feel that heat is actually because the heat from the coffee is transferring to your hands, which are cooler than the coffee. So we can measure temperature using, thermometers. And so there's a difference, right? There's a difference between what the temperature and heat, right? Temperature is a measure of how hot or cold something is, and heat is the flow of this kind of thermal energy or heat energy between different objects with different temperatures. There are different temperature scales as well. There's a temperature scale that we're pretty familiar with here in the United States, which is Fahrenheit. In chemistry lab, we usually measure in degrees Celsius. And then I've mentioned very briefly Kelvin. Remember that when we talk about Fahrenheit, right, we express that as degrees Fahrenheit. We talk about Celsius, we express that as degrees Celsius. And Kelvin, we actually don't give a degree symbol. It's just capital K. And a lot of times we think of temperature as just, measuring heat. And that is true, but it's actually measuring the average amount of energy of motion, more specific. And we call that energy of motion kinetic energy. Kinetic energy. That's the energy of motion. And we can use these different scales to kind of express those temperatures. And we can also convert between these different temperature scales. So in the US, we often use Fahrenheit, but in chemistry, we use degrees Celsius. So sometimes maybe you took a measurement and you measured your temperature in degrees Fahrenheit, and maybe you wanted to convert to degrees Celsius. Well, you can actually do that using this equation here. And again, you don't need to memorize this equation. It will be given to you on an equation sheet for an exam, so you don't need to memorize that. But you do need to know how to use the equation to solve problems. So we can use this top equation to go from Fahrenheit to Celsius or Celsius to Fahrenheit. And you can use this bottom equation to go from Celsius to Kelvin. Now, or vice versa. Now, what you can't do is go directly from Fahrenheit to Kelvin. So if you need to go from degrees Fahrenheit to Kelvin, for example, convert to Celsius first and then to Kelvin. But we'll practice this. All right, so this says convert 98.6 degrees Fahrenheit, which is our body temperature, to Celsius. And then number 2 says room temperature is about 22 degrees Celsius. Convert this to Fahrenheit. So we're going from, it looks like in the first one, we're going from Fahrenheit to Celsius. And in the second one, we're going from Celsius to Fahrenheit. So let's try this out using this equation above. So if we start with 98.6 degrees Fahrenheit. So let me just copy our equation down. And actually, I think I'm going to write this over here, just so we have a little bit more room. And it looks like we're trying to solve 4 degrees Celsius, so that's great. We don't have to rearrange this equation at all. So we have 98.6 degrees Fahrenheit minus 32. And we're going to multiply that by 5/9. And that's going to give us, remember you got to do what's in the parentheses first. So 98.6 minus 32 times 5 divided by 9. And that's going to give us 37 degrees Celsius. So 98.6 degrees Fahrenheit is 37 degrees Celsius. All right, let's try to go the other way this time. So degrees Celsius equals degrees Fahrenheit minus 32 times 5/9. This time we actually start with degrees Celsius, so we'll just plug that in over here. 22.0 equals degrees Fahrenheit minus 32 times 5/9. So we got to multiply by the reciprocal on the other side. So that's going to be 22.0 times 9 divided by 5. That's going to give us 39.6 equals degrees Fahrenheit minus 32. Now we got to add that 32 to both sides. So 39.6 plus 32 is going to give us 71.6. So degrees Fahrenheit equals 71.6. So that is the temperature. Oops, my box kind of covered my answer there. That is the temperature in Fahrenheit of 22 degrees Celsius. All right, now let's try Fahrenheit to Kelvin. So this is, again, one of those special examples where you got to go from Fahrenheit to Kelvin, which means you have to go through degrees Celsius first. So convert 98.6 degrees Fahrenheit to Kelvin. So we got to go to Celsius first, which means we're going to start with our first equation here. So degrees, and let me actually write 1 for step 1. So degrees Celsius equals degrees Fahrenheit minus 32 times 5/9. All right, so we're solving for degrees Celsius, so we want to get that alone, which is great, it already is. So now we got to just plug and chug. So we got 98.6 minus 32, just plugging our number in there, times 5/9. So 98.6 minus 32 times 5 divided by 9. And I like to put this in parentheses, that fraction in parentheses in my calculator, so that I can do it all in one step and still obey PEMDAS. So that gives us 37 degrees Celsius. But we're not quite done yet. Remember, we wanted to get to Kelvin. So in step 2, we're going to take this and plug it into our equation. This time our equation is K equals degrees Celsius plus 273. So K equals 37, right? Just plugging in that number, plus 273. And that gives us 310. And remember, we don't put a degree sign for Kelvin, we just do a capital K. So 310 Kelvin. All right, now if you wanted to convert, say you were given some number in Kelvin, or some temperature in Kelvin, and you wanted to convert to Fahrenheit, you could do the same thing, right? You just kind of do it backwards, right? You'd start with this, convert to degrees Celsius, and then use the next equation to get to Fahrenheit. All right, now what if we wanted to kind of calculate, well, how much heat is transferred when we change the temperature of something, right? So think of our coffee cup example. What if I wanted to know, hey, how much heat did that coffee cup transfer to my hands as I was holding it? You can actually figure that out using this equation here. And we'll break it down a little bit, but it's heat equals M times C times triangle T. And we'll talk about what that triangle is. So it's actually not a triangle at all. It's the Greek letter delta. And it stands for change in. So if we have something like delta T, right, like we do here, that stands for change in temperature. Change in temperature. And anytime you have the change in something, we're talking about, you know, a final temperature. What temperature were we at the end? Minus our initial temperature. What temperature did we start with? So, let's break this down a little bit further. So heat is on the left side. So that's the amount of heat transferred, right? Amount of heat transferred. And remember, when I say heat, I'm talking about heat energy, a type of energy, not a temperature, right? It's different. Temperature is how we measure how hot or cold something is. Heat is a type of energy. All right, M stands for what? What do you think? Yeah, the mass of our object. And then this C actually stands for something called specific heat. And we'll talk about what that is in a little bit. But that's what it stands for, specific heat. I don't want you to memorize this equation. You do need to know how to use it, but I will give you the actual equation, heat equals M times C times delta T, on an exam. I'll give it to you. So let me talk about specific heat, and then we'll do some examples. And that's when I think this really starts to click more. So specific heat, what is it? It sounds really weird. So every substance has this kind of characteristic specific heat, which is reported in units of calories per grams times degrees Celsius, or calories per grams times Kelvin. I know, these units look insane. And we pick which one, whether we want to use the left or the right units, depending on how we are expressing our temperature, right? Is it in degrees Celsius or is it in Kelvin? All right, so let's go over here for a second, and I want to give you a definition of specific heat. So specific heat is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. It really just depends on the phase of the substance and what substance you have. Okay, so how much heat do I actually have to put in order to raise the temperature of this substance, 1 gram of it, by a 1 degree Celsius? So you don't have to calculate this. This is always actually given to us. Chemists have done these experiments to find specific heats of these different substances over and over and over again, and now we have these nice, convenient charts that we can just look up the specific heat for specific substance and just plug it into our equation. And then just a side note down here that to just remind you that heat energy, when we talk about heat energy like we do up here, that's usually measured in calories or joules. All right, so in this chart, you can see that we have some substances on the left over here, and we have their specific heats on the right. And so you could just, you can look up whichever substance you're kind of looking at in your problem. Say you were looking at aluminum, and you can say, okay, well, I have some aluminum, and I know that the specific heat, which we represent with the lowercase c up here, is given in calories per grams times degrees Celsius, and it is equal to 0.215 for aluminum. All right, so I know this sounds a little bit wonky at first, so let's try this out. So for example, what quantity of heat is transferred when a 150 gram block of iron metal is heated from 25 degrees Celsius to 73.3 degrees Celsius? And it says, what is the direction of heat flow? And we're actually going to answer this in a moment. So let's just focus on the first part for now. All right, so I know I'm going to need my heat equals m times c times delta t equation, right? So I'm just going to note that up there. And then I think I'm going to try this over here. So, all right, so we're looking for heat, right? It says what quantity of heat is transferred. So that's what we're solving for. So I'm going to just copy out the left side of the equation. And then what's my mass here? Yeah, my mass is 150.0 grams. So I'm going to actually highlight these and color code them a little bit. How am I going to find my C value? Where can I find that? Yeah, C is actually going to be our specific heat, and we have a chart here. All right, so we have our C values here, so I'm going to just color code that there. You'll notice we're using the degrees Celsius version because that's what our temperature is measured in. All right, and then what substance do we have here? Yeah, we have iron, right? Iron metal. So we're looking for iron on here. We can ignore everything else. It looks like our C value for iron, or our specific heat for iron, is 0.108. 0.108. So let me make a note of that. C equals 0.108. And then let's not forget our units, calories per gram times degrees Celsius. All right, that's our C value. And then what's our delta T? And actually, let me write our M over here as well, so that we could just have a whole list going here. So what's our delta T? Well, we start with 25.0 degrees Celsius as our temperature, and we heat it to 73.3. So which one's our final temperature? And which one's our initial? Yeah, our final temperature is 73.3. So let's plug this in. So 73.3 degrees Celsius. And our initial is what? Yeah, 25.0 degrees Celsius. Okay, so just taking our final minus our initial. Anytime you have a delta anything, delta T in this case, you're going to take your final minus your initial. Final temperature minus my initial temperature. All right, so let's figure out what that actually is. So 73.3 minus 25 is going to give us 48.3. And that's degrees Celsius. All right, and then let's give delta T the color, we'll do purple. Purple here. All right, so our mass is 150.0 grams. Remember, always keep your units in there. Our specific heat is 0.108 calories per grams times degrees Celsius. I know those units are crazy, you guys. And then our delta T is 48.3. That's what we just found. Degrees Celsius. All right, and now it's a matter of multiplying all these numbers together, and then I'll show you how those units cancel. It's pretty nifty. All right, so heat equals 150.0 times 0.108 times 48.3, and that's going to give us 78.246. And let's figure out what our units are. All right, so noticing, right, for our mass, let me go back to blue here. We've got units of grams here. Do you see units of grams anywhere else? Yeah, we've also got units of grams in our specific heat value, right? So what you'll notice is grams is actually in the numerator and the denominator, right? These two numbers are in the denominator there, and if you don't see that, I encourage you to kind of pause the video and think about it for a little bit. So grams are in the numerator here and the denominator here, so they cancel out. I'm also noticing, right, for our degrees Celsius, we've got them over here in the numerator and over here in the denominator. So just like before, right, those are going to cancel out as well. And we're left with units of calories. Which I want you to think about, why does that make sense? Now, if we want to end up with the heat, remember that heat is expressed in units of calories or joules. Heat is expressed in units of calories or joules. So if you got all the way to the end of this, and you had some kind of weird, unit, maybe grams per calorie, or calories times degrees Celsius, or something like that, you know that you didn't finish the problem, or you didn't do something right. Because you want a unit of heat, right? A unit of heat, and that's calories or joules. In this case, calories. All right, so we also want to double check our sig figs. So I'm noticing, looks like 4 sig figs in my mass here. 3 sig figs here, and 3 sig figs here. So let's just be safe and we'll round to 3 sig figs. And that gives us 78.2 calories. All right, now our answer from above, from the above example, was 78.2 calories of heat transferred. Of heat were transferred. But if you're anything like me, you might be wondering, transferred how, right? Transferred into our substance or transferred out of our substance? And that's where heat flow comes in. So the direction of heat flow is not shown in our equation heat equals mc delta T, right? We don't have some kind of thing that indicates the direction of heat flow. If energy of the object increases, right? If we're adding in energy, right? The total energy in that object is increasing. We've added that energy in. And so the values of heat and delta T are going to be positive because we're adding in that energy. If energy is coming out of an object, the total energy of the object is going to decrease, right? We're removing energy, cooling that thing down. And the value of heat and delta T are going to be negative. And this sounds really weird at first, but let's just think about it in terms of our above example. And let me kind of clean this up a little bit. So remember that the problem said, what quantity of heat is transferred when this block of metal is heated from 25 degrees Celsius to 73.3. So are we adding heat in to our substance or taking it out? Yeah, we're adding it in, right? We're going from a cold temperature to a hotter temperature. Okay? Or you'll notice, right? When we're doing our calculation for delta T, we're starting with a larger number for our T final and subtracting a smaller number for our T initial. And that's going to result in a positive value, right? If these two were flipped, they weren't, but if they were, right? If we were cooling down our substance from 73.3 to 25, then we would have a smaller number subtracting a big number, and we would get a negative value here. Okay, so that's what this is kind of saying down below. That when you're thinking of this heat flow, if your delta T is positive, right? If you have no negative sign here, we don't have a negative sign here, right? If your delta T is positive, then your overall heat flow, right, is going to be positive as well, right? Our mass is always going to be a positive number. We're never going to have a negative mass. Our C is always going to be positive as well. And then our delta T is going to determine whether our heat is going into the system or out of the system. You can also think of it kind of big picture, right? If I went from a low temperature to a high temperature, I'm adding in energy into my object, and that object's getting hotter, its energy is increasing, and I have a positive number. If I'm cooling down my object, right? If I'm going from a higher temperature to a lower temperature, cooling it down, maybe I put it in the fridge or something, then that energy is coming out of that object. It's being subtracted, and the energy of that object is decreasing. So that's what I mean by heat flow. So when I ask for the heat flow here, how would we answer that question? What is the direction of the heat flow? I would say the direction of the heat flow is into my substance or object or block of iron, whatever you want to say there. If I cooled it down instead, right, if it was the opposite, I'd say the direction of heat flow is out of my substance. So that's what I'm looking for there. Okay, so if you have a positive number at the end, right, I don't have a negative sign there. If you have a positive number at the end, your heat flow is going to be into your substance. If you have a negative number at the end, say there was a negative sign here, then it would be out of your substance. All right, I hope that makes sense. You'll get a little bit of practice with the pod. If you have any questions, let me know.